So problem number 1 asks you to do the opposite of what we've been doing so far, which is not take a graph and tell me the equation, but here's an equation, tell me the graph. So how did you approach this problem? How do you go from this form of an equation for a line into producing a graph that reasonably depicts that relationship? What did you look at first, maybe? Let's think for a second about the slope-intercept template, that thing we've been working with today. Y equals mx plus b. According to the slope-intercept template, which this equation matches, right? The y is by itself, and all the algebra on the other side is completely simplified. According to this template, what is the value of m for this equation? Negative 1 over 4. And what does that number, what do we call that number? Call it the slope. By the way, also, when we were talking about fractions once upon a time, I made a suggestion for what to do with a negative sign in front of a fraction. What should we do with it? Let's bump it up into the numerator. So let's think of the slope as negative 1 divided by 4. So let's think about that as the slope. And then what's playing the role of b? 2. And how do we interpret that 2? What is it telling us? The y-intercept. Yeah. So that's the beauty of the slope-intercept template, is we can use it both ways, right? We can use it as something to plug a slope and an intercept that we know into, but we can also use it as a way of reading off the slope and the intercept of a line that's already come to us in an equation form. And so now that we have this information, the slope can tell us which direction that the line runs in, and the intercept can tell us the location somehow, like where this line is located in the xy plane. I find it's easiest, probably, to first think about the y-intercept. How can I use this y-intercept to give me at least a portion of where this line is located in the xy plane? What do I do with that number 2?
Since it's a positive number,
Yep.
we'll go up to y positive.
That's great. So starting from the origin, we will go up the y-axis by 2 units, and that is where our y-intercept for this line is going to be located. So there is a point on this line right there. So it has the coordinates 0, 2. So that's how we use the y-intercept as information, right? We know that that purple point here is going to be a point on our line. Now that we have one point on our line, how am I going to find a second point? Yeah. Now we have to follow the slope, right? The slope is one other way of finding another point on this line. So let's decode the slope. Remember, every slope is what divided by what? It's rise divided by a run, right? In the vernacular, that's what we call it, rise over run. And so this negative 1 and this 4 are telling me how to get from one point on this line to another point on this line. What's the negative 1 telling me to do? Go 1 unit in which direction? Since it's a rise, it's a vertical direction. Since it's negative, that means go down, right? So how I would interpret this is go down 1. Right? So over here on my picture, I'll go down by 1 from my y-intercept. And then what about this 4 in the denominator? What's that telling me to do? Which direction is that 4 going to be? Up, down, left, right. Right. It's a run, so it's a horizontal direction, and it's a positive 4. That means it's a rightward direction. Right. So as y decreases by 1, x increases by 4. And once I do both of those things, that gives me a second point on the line, right here. And in case we're interested, the coordinates of that point would be 4, 1. And as soon as I have even just 2 points, basic tenet of Euclidean geometry is that that is enough for my line. And all I have to do then is just draw my line that goes through those 2 points. So that's a pretty good recipe for how to use the slope to find a graph for the line. Start at your y-intercept and then take apart the slope to decide how to use its rise and its run separately to find the location of the second point. One other option that we have here is it could also have used a data table. This is an underrated option, but I kind of like it. In our data table, because our y-intercept was 2, we know that there's one point on the data table, 0, 2, that we know for sure from the beginning. And if I want to find a second point, all I have to do is choose a second value for y. And looking at this equation, I'm probably going to want to choose values for x. Sorry, let's find me a second value for x. I'm probably going to want to choose a value for x which will succeed in clearing this denominator and giving me a whole number. I don't have to do it that way, but that way will give me some nicer arithmetic. And so maybe I want an x which is a multiple of 4, so that when I multiply it by 1/4, I get a whole number. So if I did happen to choose x equal to 4, then the y value that I would get would be negative 1/4 times 4 plus 2. And doing out this arithmetic, negative 1/4 times 4 would give me negative 1. And negative 1 plus 2, give me 1. And sure enough, that's the coordinates of the other point right here. So that's another way of doing it, that instead of thinking geometrically and graphically about taking the slope apart, we can just think numerically about plugging in another x value and finding another point. And as soon as I have 2 points, I can just draw the line straight through from there and be done. Unless the problem asks us to label a third point, in which case, yeah, we'd want to label a third point.